We have here a digital elevation model freshly downloaded from a government GIS website. The data is in the original lat-long coordinates. When you work with a new DEM for the first time, it is a really good idea to check the DEM for potential errors. The easiest thing to do is a visual inspection using hillshade and slope analysis. Let's take a look. When we turn the hillshade on, which is already set to a transparency of 50%, we see that most of the area is very darkly shaded, so never sees the light. That is something that seems to be unrealistic for this part of the Rocky Mountains. Let's look at the slope. When we turn on the slope, in this case here, red slope is the steepest slope above 85 degrees. Remember that 90 degrees is vertical, is straight up. We see again that a very large proportion of our area is in the red category with extremely steep slopes. This doesn't make much sense. So, do you have an idea what is going on here and what we can do to correct this? The problem lies in the fact that the elevation model from which we derive the slope and the hillshade is in lat-long. That means if we go to the raster information and we look at the grid cell size, it is a very small value. It is a very small value because our spatial reference is in lat-long and the units are in degrees. So what we have here is a cell size which units are expressed in degrees. So 0.0002, so that is 2/10,000ths of a degree. That is probably around 25 meters on the ground. So let's look at this in an Excel spreadsheet. We know that slope needs rise over run. Let's assume right now that our rise is 1 meter and our run in this case, because we're not looking at units, is 0.0002. The equation to calculate slopes in degrees is to take the arctan of rise over run, and because this results in degrees in radians, then we have to adjust for that and going back to degrees. So the conversion of radians to degrees is 180 divided by pi, or just a conversion factor. And so here is our equation, arctan 1 divided by 0.0002, and then here's our conversion factor. And so our degrees with this rise over run is almost 90 degrees. It's almost vertical. And of course that makes sense. A rise of 1 meter over something that is 2/10 of a millimeter wide, of course, is almost vertical. So the problem lies in the fact that we're mixing units. We're mixing right now meters with degrees, and that we must avoid. So therefore we shall never derive slope, or hillshade for that matter, from an elevation model that is in lat-long. So that means we have to project our raster file. We would go to the project raster tool, fill in our input raster, have an output raster data set, define our coordinate system, in this case it's UTM, and accept the rest of the default values and hit run. The result looks something like this. Here's our elevation. Here is the same hillshade that we derived. Now we see more areas in a lighter region, but the hillshade has some striping issues. So something went wrong that isn't really in the terrain. Let's look at the slope. The slope also has these striping issues in both directions, vertical and horizontal, or east-west and north-south. So this is something to be concerned with, and you would not want to use this kind of projected elevation model for any further analysis or for display purposes. So what went wrong? What went wrong is that the sampling technique for your raster projection is the nearest neighbor. And I will explain later why the nearest neighbor results in these striping issues. We have other options. We also will look at the bilinear interpolation and at the cubic convolution interpolation. Let's look at bilinear. Here's our elevation model. Here's our hillshade. For the first time we see a hillshade that makes sense. We can clearly see the ridge line, and we can see valleys down here. And when we turn on the slope, then now also for the first time we can see some steeper slopes as we expect, but most slopes are in the sort of medium range in this part of the Rocky Mountains. We are satisfied with the bilinear interpolation technique, this one here. When we use the cubic convolution, the results look like this. Our hillshade hasn't changed much, but we can see a little bit of striping here and there, and our slope does not make any sense at all. We have the steepest slopes along the ridge lines, on top of ridge lines. That is something that shouldn't happen, and again, this resampling technique must be avoided. So to summarize, when you use the raster projection tool and you are projecting continuous data sets, then you must use the bilinear interpolation as your sampling technique. It says here, suitable for continuous data, while the nearest neighbor is suitable for discrete data, such as, for instance, land cover code 1, 2, 3, 4, 5, or soil type A, B, C, D, E. And whilst it states that the cubic convolution is also suitable for continuous data, we can see that it does not work for elevation models. Let's quickly compare the hillshades. We have here the hillshade from our original lat long. Here's the hillshade using nearest neighbor. Here's the hillshade using bilinear interpolation. And here's the hillshade using cubic convolution. You see very small difference between the last two, but noticeable. And then of course we can also compare our slopes. Original, nearest neighbor, bilinear interpolation, and cubic convolution. That's all for today. Until next time.